Welcome everyone to today's PCS-IBS seminar. It's a great pleasure to have with us today Miguel Gonçalves, and I would like to invite our scientific host, Alexei, to introduce our speaker. Please, Alexei.
Okay, yeah, thank you, Tilan. So, as Tilan has already announced, we have Miguel Gonçalves today talking about hidden dualities in 1D quasi-periodic lattice models. So Miguel is currently doing his PhD in Instituto Superior Técnico, where he joined since September 2019. He's working with Pedro Ribeiro and Eduardo Castro, and his interests are focused about topological condensed matter models, disordered models, well, as we will hear in this talk. And so with this, Miguel, please, the screen is yours.
Okay, so thank you very much, Alexei and Dylan, for the very kind introduction. And I would like to thank the organization for the opportunity to talk in this very nice series of seminars. So today I'm going to tell you about our recent work, which is entitled Hidden Dualities in One-Dimensional Quasi-Periodic Lattice Models, that you can find here in this archive preprint that will appear throughout the presentation. So feel free to ask me questions during the presentation if you have any doubt. Okay, so let me start by mentioning the driving force of this work, which was done in collaboration with Professor Bruno Amorim from University of Minho, Professor Eduardo Castro from University of Porto, and Professor Pedro Ribeiro from University of Lisbon. So Professor Eduardo and Pedro are actually my PhD supervisors. Okay, so I will start by giving a general introduction on quasi-periodic systems before focusing on the main purpose of our work. So these are systems that break translational invariance, but they do it in a deterministic way. So they are inhomogeneous systems, but they are not disordered because they are associated with these long-range spatial correlations. So here I decided to divide these systems into types that I'm calling here these extrinsic quasi-periodic systems and also intrinsic quasi-periodic systems. And they are actually not that different, at least conceptually, but they are studied in rather different areas in physics. So we will start with these perhaps more classical systems with extrinsic quasi-periodicity, in which what we typically are thinking about is some ordered lattice that I'm representing here with this black site. And then we apply some potential here in blue with a wavelength which is incommensurate with the lattice. So this means that if you divide the lattice constant by the wavelength, you get an irrational number. Now, if you evaluate this potential at each site, you will be attributing on-site energies that will never repeat throughout space. And that's just a consequence of the incommensuration between the potential and the lattice constant. Now, these systems are very interesting because they give rise to highly non-trivial localization properties, even in one dimension. So we can have, for instance, transitions between an extended phase in which the wave function is extended in real space, and the localized phase where the wave function is localized around some region in space. And this can happen even in one dimension, which is not the case, for instance, for disordered systems, for which in one dimension we always have localization. And actually, this transition between an extended and localized phase was already observed experimentally around more than 10 years ago, both in optical and photonic lattices. So in the first case, through the localization of a cloud of cold atoms, so as a function of the intensity of this quasi-periodic potential, they were able to observe a cloud of cold atoms localizing as time went by. And in the case of photonic lattices, what we are able to observe is the localization of light instead. So here the quasi-periodicity is incorporated, is engineered here in the photonic waveguides. Okay, so this of course there are many references, important references that appear after these ones. These I would say are the pioneering ones. But let me now go to the other side and talk a little bit these intrinsic quasi-periodic systems, which are perhaps the more recent, have been a subject of more recent attention. And these are nothing else than the so-called Moiré systems, okay, that you probably already heard a lot about. And the simplest example of that is this, in one dimension, is this system where we consider two chains of atoms on top of each other, but these chains have incommensurate lattice constants, which means that if you divide one by the other, you again get an irrational number. So this means that the hoppings, the interlayer hoppings, will never repeat through exactly throughout space, even though they may be very similar in different regions in space. Now, the two-dimensional, the most well-known, perhaps two-dimensional generalization of this type of system is actually the twisted ballet graphene, in which we have two graphene layers on top of each other, and then we rotate them. And it's this rotation that really introduces here the quasi-periodicity in the case of twisted ballet graphene. So we get these Moiré patterns, and the system for a generic angle will be truly quasi-periodic. Now, this system has a lot of interesting physics behind, so namely the existence of this very narrow band, very narrow energy band for some so-called magic angles. And precisely at this narrow band, it was observed that superconducting and correlated insulating phases exist, and also very interesting topological properties that I'm not going to cover here. So I would just like to make here an important comment, which is typically when people are studying theoretically these Moiré lattices, they actually neglect effects of quasi-periodicity and assume that the system is really commensurate. And this is true actually for some specific set of discrete angles, but in general, the system will be truly incommensurate. Of course, even with this description in terms of a commensurate structure, people are already able to understand very important physics of this model. But this paradigm on the effects of quasi-periodicity on twisted ballet graphene is changing a bit. And this recent reference, which is our reference, is an example of that, in which we study effects of quasi-periodicity in twisted ballet graphene at the single particle level, precisely in the narrowband regime. And we show that they actually have important consequences to the wave function localization properties. Okay, so, but of course, more recently now, our works are starting to appear at the interface between these two types of systems. And an example of that is this very nice recent work on photonic Moiré lattices, in which as a function of the lattice, or depending on the lattice incommensuration or commensuration that is built in these photonic lattices, we can either observe localization of light or not. Okay, so this was just to give you a general overview, but in fact, what we will be interested what we were interested in our work was to try to describe these simpler one-dimensional quasi-periodic systems in order, of course, to in the future try to understand the more complicated cases. So we here really wanted to fully understand the phase diagrams of these systems. Okay, and of course we cannot talk about one-dimensional quasi-periodic lattice models without mentioning the paradigmatic example and the pioneering example, which is the Aubry-André model. So this model enters the class of intrinsic quasi-periodic systems that I mentioned to you before. And so it's a very simple model of this type. It only has nearest neighbor hoppings that are included here in this term. And then we apply this quasi-periodic potential, which is this cosine of 2 pi tau n. And this tau is really what's introducing here the quasi-periodicity, because it is an irrational number. So if you set the lattice constant to 1, this tau will be just the inverse of the wavelength of this blue potential. Okay, and then we have this phase phi, which is just a shift of the quasi-periodic potential with respect to the lattice. So this doesn't seem to matter that much, but actually we will see that it will be of central importance in our description of these one-dimensional quasi-periodic models. Now, just to show you the phase diagram of the Aubry-André model, let me just stop here a bit to tell you what this IPR is. So this is just it will appear throughout the presentation, and this is just the inverse participation ratio, which is the second moment of the wave function. And this quantity typically, when it's large, it signals localization, and when it's small, it typically signals an extended phase. Now, in the Aubry-André model, what we have is a transition between an extended and localized phase for V over T equals 2. Okay, so this transition is energy independent for the Aubry-André model. And of course, in the extended phase, we have a wave function that is extended in real space. And in the localized phase, it's exponentially localized around some region in space. And in the case of the Aubry-André model, we know exactly what's behind this transition, which is an exact duality that exists between wave functions in the localized and extended phase that are related just through a modified Fourier transform. So the modification is just this tau, that is the same tau that appears here in the quasi-periodic potential. Curiously, exact at the critical point, the wave function is equal to its Fourier transform, and we have these very interesting multifractal states. Okay, but the problem is now, so when we go a little bit away from this limit, from the case of the Aubry-André, what typically happens is that we start having these so-called mobility edges. So the transitions between the localized and extended phase starts depending on energy, which was not the case in the Aubry-André model because it occurred for V over T equals 2 independently of the energy. So this is what typically happens. And there are some few fine-tuned models for which we can understand fully and analytically these phase diagrams. And these are just two examples. There are not much examples where we have this understanding. And in this case, for instance, what's behind these mobility edges is really a duality, which is a generalization of the Aubry-André duality. Now, if we move away from these limits, from these, let's say, fine-tuned limits for which we know how to treat exactly, things get a little bit more complicated, and we don't even need to consider generalizations that are different from, for instance, the Aubry-André model. So if you consider, for instance, just a term with next nearest neighbor hoppings to the Aubry-André Hamiltonian, you can see, and that was done here in this reference, you can see that as a function of the intensity of the next nearest neighbor hopping, the phase diagram becomes less and less trivial. So here we are looking into the IPR results again, and we have this transition between the extended black phase and the reddish yellow localized phase. And we can see that as we increase the T2 over T1, which is the next nearest neighbor hopping over the nearest neighbor hopping, we get a less and less trivial phase diagram as we do that, and this phase transition between the extended and localized phase becomes complicated, and we don't know how to describe it without using these numerical methods, for instance, computing the IPR for large system sizes. So, of course, this gives rise to two important questions. The first one is, why are these models for which we have this exact understanding special? What's the relation between them? And the other is how, and perhaps more fundamental, how can we really understand localization, delocalization transitions in generic models? Okay, so these are essentially the questions that we wanted to answer with our description. Okay, so now I will start telling you about our approach to this problem, which essentially uses this so-called commensurate approximant of our quasi-periodic system. And to start, let me recall or tell you that any irrational number can be written in terms of an infinite continued fraction, as I'm showing you here. But of course, you can truncate this fraction at some order. And if you do that, what you will get will be a rational approximant of your irrational number tau that I'm calling here tau c. And this approximation will be given by the ratio of two co-prime integers that I'm calling here n1 and n2. Now, to give you a bit of intuition on why this matters to us, so suppose I will use here the model of the Moiré ladder, so of the two chains on top of each other, just to show you, to show you some picture. And suppose that we want to approach a ratio between the lattice constants, which is in this case the inverse of the golden ratio. So we can approach that ratio by considering different commensurate approximants. For instance, we can start with this one, which is truncating this continued fraction expansion at some order. And we see that in this case, the ratio between the lattice constants is 2/3, which means that we have a unit cell with 3 sites in the upper layer and 2 sites in the lower layer. But of course, if we want to get a better and better approximation of the irrational number tau, which in this case is the inverse of the golden ratio, what we will need to do is to increase further and further the unit cell. And of course, in the really incommensurate and quasi-periodic limit, we should take the unit cell to infinity, okay? But that's not exactly what we do in our approach. So instead, what we do is we look into each of these commensurate approximants, which are infinite systems with well-defined unit cell, and study their energy bands. Okay, so essentially, what we do is we study these commensurate approximations and see how their energy bands change in the different phases of the limiting quasi-periodic system. And regarding that, there are a couple of points that are important and that I want you to become aware of. And to show you that points, let me use here this animation, which again uses the Moiré ladder. And what we are seeing here is just the energy bands of this system, this infinite system, with a unit cell that I'm defining as this unit cell within this dashed box. So in this case, we have 5 sites in the unit cell, which means that we will have 5 bands, 5 energy bands. And of course, the first point that I want to mention to you is that these energy bands depend on the shift between the sites in the lower layer and in the upper layer, okay? And this is natural for a commensurate system because if you consider that the hoppings, the interlayer hoppings are modulated, for instance, that they decay exponentially with the distance, it's natural that if you do these shifts, the hoppings within the unit cell will effectively be different for different shifts. Okay, so that's why we see this dependence on the shift between the sites in the lower and upper layers. And also, you can see that there is here a periodicity where the energy bands will repeat after some shift. And this can be actually understood again from this animation, because so we start with this configuration here, where this site is aligned with the site in the layer above. But anytime that a site in the lower layer aligns with the site in the layer above, we are just making a redefinition of the unit cell. Okay, so that we should recover the same energy bands because it's just a unit cell redefinition. Now, of course, if our unit cell is very large, we will have many ways of aligning the sites in the lower layer with the sites in the upper layer. And therefore, this period will become smaller and smaller as we increase the unit cell. So this argument can be, of course, generalized to Aubry and André-like models. So in that case, you can just see the maxima of the potential as this triangular site in the lower layer. And in this case, a similar thing happens. So if we plot the energy bands as a function of this phase phi, which if you remember is exactly the phase that entered as a phase in the cosine term in the case of the Aubry and André model, what you will see is that the energy bands have a periodicity which is actually 2 pi over the number of sites in the unit cell that I'm calling here N1. So in this case, we have a unit cell with 4 sites, and therefore the period as a function of phi will be pi over 2. Okay. So having said this, we just need to study a single period of this energy dispersion because all the others will be equal. So we define this new variable calligraphic phi, which is such that when it runs from 0 to 2 pi, it covers a single period of the energy dispersion. Okay. So what we will be studying and what you will be seeing now in the next slides will be energy bands that will be studied not only as a function of momentum, but also as a function of this real space shift phi. So we'll be seeing things like this. Instead of studying energy bands just as a function of momentum in one dimension, as we are enhancing the dimensionality of our system using this real space shift phi. Okay. So in order to try to get a little bit of intuition on what is happening here, I will use the Aubry-André model. And what we will be seeing here is how the energy bands in this enhanced space look in the different phases of the limiting quasi-periodic system. So in this first row, we are looking into a commensurate approximant of our quasi-periodic system that only has a single site in the unit cell. And in this case, in this lower row, we are looking into a commensurate approximant that has 8 sites in the unit cell, and I'm choosing just one of the 8 bands at random. The others will have a similar behavior. Okay, so let's start by looking into this case where we have 1 site per unit cell. So if you look at the counter plot in the extended phase, the bands are essentially concentrated on K. That in the localized phase, the counters are essentially localized on phi, and this means that we have a small phi dependence in the extended phase and a small k dependence in the localized phase. However, if you look exactly at the critical point, you can see that the dependence on k and on phi is essentially the same. So we have this equal dependence on k and on phi, and we see these Fermi surfaces that Fermi surfaces in this generalized space. Okay, so these generalized Fermi surfaces seem to be invariant under switching k and phi precisely at the critical point. Okay, but now we can increase the size of our unit cell and see what happens. And if you look with attention, so if we again start in the extended phase, we see that the dependence on phi essentially becomes irrelevant in the extended phase, and the dependence on k also essentially becomes irrelevant in the localized phase. So only very close to the critical point we have a mutual dependence on phi and on k, or a significant mutual dependence on phi and on k. And precisely at the critical point, we seem again to recover this invariance under switching this phi with k. Okay, so this actually, this very simple picture already allows me to tell you one of the central results of our study, which is what we found was that what we are seeing here in the Aubry-André model actually happens in more generic one-dimensional quasi-periodic systems. Okay, so we have this, if we are close enough to criticality, of course, and if we are using an approximant with a large enough unit cell, as we will see in a bit. But essentially what happens is really that in the extended phase, the phi dependence becomes irrelevant as we increase the unit cell. And in the localized phase, it is the k dependence that becomes irrelevant. And precisely at the critical point, we have this invariance under switching k and phi. So we have these universal Fermi surfaces that are really scale invariant. So they have this shape irrespectively of the approximate. Okay, so to give you an example of that, I'm going to use here the Aubry-André model with next nearest neighbor hoppings. And so here I'm just plotting the energy bands for some approximate, which in this case has 21 sites in the unit cell. But this is a little bit messy, so let's focus on one of these energy bands that we are seeing here. And so what matters here is that the energy bands that we are looking at is bounded by this black line and also this blue line. So what we want to do here is just to study the Fermi surfaces in this generalized phi and k space for different points within these energy bands. And what I'm plotting here in red is precisely the mobility edge of the limiting quasi-periodic system. Okay, so this is the phase boundary between the extended phase that should be here and the localized phase that should be here. And what we see, if we plot the different Fermi surfaces at different points, is that precisely when we cross the critical point, which are these points that I'm showing you here in the middle panel, what we have is this invariance again under switching the phases phi and k. So notice that I'm plotting here in blue the Fermi surfaces with phi in the x-axis and k in the y-axis, and then in dashed red I'm just switching these phases, and you see that precisely at the critical point we have this invariance under switching. Okay.
Ask you a question, please.
Sure. Yeah, of course.
So if I understand correctly, we talk here about some rational approximations now to the Aubry-André chain, and still you say. So my question basically is whether the how should I say that? Whether the self-dual point of the model itself is also present in this. Yeah, it is, right?
It's manifested really in this invariance under switching k with phi. The self-dual point.
Right. So if you choose a rational approximation to this, whatever, forgot what you were calling this alpha or beta or whatever. Normally, so to say, normally a rational number. If you give this a rational approximation, you still keep the duality and the self-dual point, correct?
Yeah, that's it. But there's an important point, which was what I'm going to tell you now. This happens in general if your approximant has a large enough unit cell. So you may have cases where for a small unit cell your energy bands may be very complicated, and
Wait, you go too fast. My question is just, so I do a rational approximation, but I still keep the dual, the symmetry, the duality.
Yes, but
I do, right?
But in this, it's only manifested. So this duality in these rational approximations is manifested by this change, this invariance in the changing k and phi. But
right.
This, No,
what about the self-dual point?
But the self-dual point
must also be still there, right?
It's there, but I mean it's so it depends what you mean by so the self-dual point that we are used to define is really in the quasi-periodic limit, right? So in the case of the Aubry-André model, it will be at v equals 2.
So you want to say that there is so if I do a rational approximation, then I keep the duality property, but I lose the self-dual point. Is that what you say?
In general,
there's a point where the transformation, as you explained it, the Fourier transformation will bring you back to where you started from, so to say.
Yeah. In general, you may lose that self-duality if your approximant doesn't have a large enough unit cell. Yeah. In general, it's what we think it happens, and only when you increase enough your unit cell, you will get this nice invariance that it's really manifesting this self-duality in the switching phi and k.
But then it should never recover unless you really go to the quasi.
Yeah, it recovers in an exponentially good way. So of course, only in the limit of the infinite unit cell you will have this perfect invariance, but you can already see it for fairly small unit cells in many cases.
So then this symmetry which you talk here about, is that the cell that at this transition at the self-dual point, is that an approximate symmetry or is that a precise symmetry?
It depends on the model. So there are models where you will have, so for instance, in the Aubry-André model, you have this symmetry independently of the approximate that you are considering. That's so if you look into.
Yeah, but that's what I was asking. So I'm talking just about Aubry-André.
Just Aubry-André. Yeah, Aubry-André. Yeah, you always have. I thought you were talking in general. No, of course, yeah. In Aubry-André, you always have this symmetry independently of the approximate. Sorry, I thought that you. Yeah, that's an important remark that I'm going to tell now. So there are these special models that we are going to see where we always have this symmetry at the self-dual points under switching the variables k and phi independently of the approximate. But in general, that's not what happens. Okay, so in general, you may have more complicated situations And that's what essentially what I'm showing here with this picture. So in general, around criticality, what you may have is that the energy bands may look very complicated if you are commensurate approximate as a small unit cell, right? Which I'm showing here just an example. But if you increase your unit cell enough, what you will have will be these energy bands flowing into these very simple energy bands, which are essentially host Fermi surfaces that are essentially sinusoids in phi and k. So they are just these very simple universal Fermi surfaces that we are seeing here as examples in this picture. But of course, there are, as I told you in some of the previous slides, there are these models that have these mobility edges that have an exact solution, okay? And those models are precisely the models in which these dualities between the phases k and phi seem to arise from the simplest possible commensurate approximant, just like in the case of the Aubry-André model, as we were discussing. So in that case, you take an approximant with one side per unit cell, and you already see this duality in switching k with phi. But also what we have seen is that in these models, what seems to be common among these models that have this exact solution for the mobility edge, and here are some examples, is that this invariance under switching k and phi arises from really the simplest possible commensurate approximant, just like in the case of the Aubry-André model. And here is an example in which we have some exact mobility edge or analytical mobility edge that you can compute by looking into an approximant with one side per unit cell and just requiring these invariants under switching k and phi, and you immediately get the condition for the analytical solution for your mobility edge, which is quite remarkable. But of course, we have, in general, this is not what happens. In general, we have more complicated scenarios. As I told you, in these cases, in these more generic cases, what we have is dualities in these phases phi and k that arise only as the unit cell is increased enough, okay? So they are only arise in the limit where the unit cell goes to infinity. But in these cases, so in many cases, you don't have to increase that much the unit cell in order to already see essentially perfect duality. And in those, so the Aubry-André model with next nearest neighbor hopping is an example of that. So here we are seeing the phase diagram obtained through the inverse participation ratio for a large system. Then what I do on top of that is to compute these so-called analytical SD curves, the analytical self-dual curves, for which and I do this for an approximate with 8 sites in the unit cell. And here we already have an essentially perfect duality under switching k with phi. So we can give this very nice analytical approximation to the phase boundary, which seems to be to be where we should expect the mobility edge to appear. Of course, in general, we may have a more complicated situation, and we may lose analytical trackability. But even in those cases, we may still compute these points of invariance under switching k with phi numerically. And that's what I'm doing here in this example of the Moiré ladder. So you can see that the phase diagram is highly non-trivial. So we have these re-entered behaviors between extended and localized phases. And on top of that, I'm plotting these self-dual points, the points that are invariant under switching k and phi, in this case for an approximant with 34 sites in the unit cell. And you can see that they match very accurately these mobility, the places where you should expect a mobility edge to occur, okay? So,
can I ask a question?
Sure.
So on the Moiré ladder case, it looks like when eta, I don't know which one is, but that's like some parameter that tunes the quasi-periodicity. It looks like a plot goes from red to blue on the high energy and very low energy. So it's localized to extended transition. That what you're seeing? Can you comment on that?
Because this chi is so we are modeling the hoppings, the interlayer hoppings through a Gaussian. So we say that they decay with a Gaussian in the distance between the hoppings. So this chi is really the length associated to that Gaussian decay. Okay, so that's why for a small chi you get this. Typically, you get more localization. The quasi-periodicity effects are enhanced, and for a larger chi they are reduced. But you can have less trivial things like these reentrant behaviors. Yeah.
Okay, I see. Thank you.
Yeah. You're welcome. Okay, so this essentially closes the first, I would say, central result of our work. But now, in the remaining time, I would like to discuss a little bit I would say the second central result of the work, which is essentially an attempt to answer this question that you probably already had, which is what's really behind this duality in the phi and k phases. So, of course, intuitively, we know that phi is encoding these real space shifts in quasi-periodicity, and k, of course, is a momentum. So this duality may be encoding some duality between real and space and momentum space. And that's exactly the answer that we reached. So essentially, in short, what we found was that there are hidden dualities that map wave functions in the extended and localized phase, exchanging the roles of phases phi and k. So precisely at the critical point, the wave function is mapped into itself, and we have these invariants under switching k and phi. Now, I will try to give you just a sketch and a general idea on the way that we defined the duality transformation. So we provided a definition for duality transformation also by making use of these commensurate approximations. And for this discussion, I will have in mind Aubry-André-like models. So again, these models where we have an ordered lattice and then we apply this quasi-periodic potential. So the first thing that we need to do is to choose an approximant with a unit cell that is large enough so that we are already in this limit where the Fermi surfaces that we are seeing in our commensurate approximant are essentially these simple sinusoids in phi and k. Okay. So when we are in this limit, and this only happens if we are close enough to criticality, okay, what we can do is we can define these dual points in the extended and localized phases of the limiting quasi-periodic system. And these dual points, if you look at the Fermi surfaces of each of these dual points, they will be related just through pi over 2 rotation in this phi and k plane, okay? So it's just a suitable change in they are related under a suitable change in the variables phi and k. And that's what really defines these dual points. Now, in order to make more progress, we need to recall some important thing that I already told you in some of the previous slide, which is if we look into the energy as a function of this phi the non-calligraphic phi, which is just the phase that encodes this shift in the quasi-periodic potential, which see that the energy bands will be we'll have a period which will be 2 pi over n1, where n1 is the number of sites in the unit cell. And remember, that's how we define this calligraphic phi to cover only a single period of these energy bands. Now, what I didn't tell you is that even though the energy bands will be equal in each of these periods, the wave function will be slightly different. And the difference is really kind of trivial because the wave function in each of these periods will be just a cyclical translation, or all the possible cyclical translations of the wave function with respect to this psi r, the wave function in the first period. And this is simple to understand if you remember that making these shifts of 2 pi over n1 is just making different redefinitions of the unit cell. So the equivalent of, for instance, the first site in the case where phi equals 0 will be a different site in the lattice when phi equals, for instance, 2 pi over n1. And of course, the wave function will have to shift accordingly. Okay. So what we are seeing, just to again reinforce, is in each of these periods we have all the possible cyclical translations of the wave function, which are of course n1 cyclical translations if we have n1 sites in the unit cell. Now, what happens, and here I won't be as detailed, but what happens in momentum space is a similar thing, But in this case, for this function psi d, so for this wave function psi d. So this is just the, it's defined here, is just the Aubry-André Fourier transform of the wave function psi r. And notice that I'm defining it for a given commensurate approximant, so the sum is restricted to n1 terms. And instead of tau here, I'm using the rational approximation of tau, which is tau c here. Okay, but this is just the Aubry-André Fourier transform for some commensurate approximant. And if we plot, so let me tell you what I mean by this different case that I'm using here, because they are actually different, and this is important. So this calligraphic K, which has been appearing throughout the presentation, is actually the momentum measured in units of our true unit cell, so the unit cell of our commensurate approximant, okay? And this K, the non-calligraphic K, the normal K, it's just the momentum measured in units of the lattice constant of the original lattice without applying the quasi-periodic potential. So of course, if we look into how the energy bands behave as a function of this non-calligraphic K, we will see that they will repeat in periods of 2 pi over the number of sites in the unit cell, because of course this is the Brillouin zone, the true Brillouin zone associated with our commensurate approximant. But I mean, in a similar way to what happens in real space, in each of these periods, if you look into this Aubry-André dual wave function psi d, you will again have all the possible n1 cyclical translations of this wave function psi d when you run this normal K from 0 to 2 pi. Okay, so this is not obvious. I'm not giving all the details. I just want to give here the general idea. Because with this in mind, the duality transformation that we define is a statement that the wave function psi r is a statement that relates the wave function psi r with the wave function psi d, but also all the possible cyclical translations of psi r with the respective cyclical translation of psi d. Okay, so this is the general idea, and it relates these wave functions precisely at the dual points that we can find through this spectral duality in the energy bands of as a function of phi and k. So just to be a little bit more formal, these 2 points were what I already told you. Here I'm just defining this Aubry-André Fourier transform in terms of this matrix U. So psi d will be just U dagger times psi r. And what we can do here is to define this duality transformation matrix that I'm calling here OC, such that when it's applied to any of the possible cyclical translations of psi d, it gives the respective cyclical translation of psi r. So this T is just an operator that implements this cyclical translation in the wave function. Now, after doing, so this is at dual points. Recall that this psi d and psi r are defined at dual points, as shown here in the figure. So what we can do now is to try to see what are the properties of this matrix OC that we just defined. And it's easy to see that it's actually a circulant matrix, which means that each row is just a cyclical translation of the previous row in this matrix. And therefore, it can be diagonalized by a Fourier transform matrix that we use here to be the Aubry-André Fourier transform, this matrix U. So this chi-c will be, of course, a diagonal matrix containing the eigenvalues of OC. And therefore, information of different duality transformations will be contained in this matrix chi-c because the U's will be always equal. And of course, what we want to do in the end is to take the limit, the incommensurate limit, and that means taking the unit cell to infinity, or in other words, taking this rational approximation tau c into our irrational number tau. And what we are assuming is that in that limit, this matrix chi-c defined for some rational approximant will go to this other matrix chi, which is an infinite sized matrix. So recall that this matrix chi-c is just n1 times n1, where n1 is the number of sites in the unit cell, because this matrix OC is also that has also that dimension. But in the limit where the unit cell goes to infinity, we'll have this infinite sized matrix chi. And if we do these definitions, our definition for the duality transformation reduces to this very simple form. So it's just an Aubry-André Fourier transform here implemented by this matrix U, and also then plus this diagonal matrix chi. So when we apply this transformation to the wave function at some point P prime, we will get the wave function at its dual point P. Okay, so this is so just by requiring that this duality transformation should map all the wave functions psi r to psi d and their cyclical translations, we get this very simple definition for the duality transformation. And quite remarkably, for the models for which we have an exact expression for the duality transformation, which is actually a generalization from the Aubry-André duality, the transformation that they found can actually be written in this very simple way. Okay, so of course, I'm not going to enter into much details, but of course this chi is an infinite matrix, and we can, so information on the entries of this matrix chi can actually be encoded in this periodic function of this continuous variable that I'm calling here x. And I'm not going to enter into details on why this is the case, but I will give you examples of this function. And starting with the Aubry-André model, in which this chi matrix is just the identity. So the duality transformation in the Aubry-André model is just applying the Aubry-André Fourier transform, which is this U dagger here, and we get the wave function at the dual point. And so the entries of this chi matrix can be encoded in this function chi of x equals 1 simply. Then we can look into one of these models for which the duality transformation is known exactly. This one already appeared in some previous slides. It was one of the cases that had these exact mobility edges. And it doesn't really matter much the form of the function, but in this case, what matters is that this chi is not really the identity matrix, it's something more complicated. And now it depends on some parameters of the model and has this cosine of 2 pi x, which renders this function chi of x periodically. So now in the next slide, the relation between the entries of this matrix chi c that we can define for a given commensurate approximant and this thermodynamic limit function chi of x will become more clear. Okay, so precisely in this plot. Of course, what we did in order to try to test our definition for the duality transformation was to apply it to cases where this function chi of x is known exactly. And of course, the example that I just gave you in the previous slide is one of those cases. So what we are doing here in this plot is we chose some regime of parameters, and we are plotting the function chi of x, the thermodynamic limit function chi of x for those parameters, and it has that analytical expression that you just saw in the previous slide. And then we are defining this matrix chi c, which is of course defined for a given commensurate approximant. And I'm doing that for different approximants. So in this case, it is for an approximant with 13 sites in the unit cell. And what you can see is that the entries of this diagonal matrix chi c will be actually the n1 possible evaluations of this function chi of this thermodynamic limit function chi of x. So this will be, in this case, we have 13 sites. So we will have 13 points of this function chi of x. And these are just these 13 equally spaced evaluations of the function chi of x. Now, if we increase the number of sites in our unit cell, we will be also increasing the number of sampling points with which we will be sampling this function chi of x. And that's what I'm showing you here. In this case, we have these 55 sites in the unit cell, and therefore we have 55 sampling points. And of course, if you increase even more your the unit cell of your commensurate approximant, you will be covering more and more all these region and all the values in x. And of course, in the limit of an infinite unit cell, we will be covering completely this interval of x from 0 to 1. Now, this is actually a very nice result, because it not only told us that our definition for the duality transformation actually makes sense, but now we can also apply it to cases for which it is unknown. Okay, so there are these very special cases for which we know a duality transformation to exist, but in general we don't know how this duality looks like. And just to show you some example in which we did that, I will again show the Aubry-André model with next nearest neighbors, in which we defined this duality transformation matrix chi-c, okay, for different regions of the phase diagram. And what we are seeing here is the definition of this chi-c for or the entries of this chi-c, the plot of the entries of this chi-c for different regions in the phase diagram. For instance, here, using these dual points around this region in the phase diagram, we define this in this duality transformation. Then using these points here more in close to zero energy, we define this one, and here using these green self-dual points, we define this duality transformation. And the message that I want to pass here is that even though there are some regions in the phase diagram where the duality, these entries seem to be flowing into some quite nice duality transformation, so some quite nice thermodynamic limit function of x. In general, what we will see in other places in the phase diagram will be things like this. So this is quite chaotic. So this is the case here close to zero energy, but in general, we will be seeing chaotic things like this when you are defining your duality transformation. And you can see that this is full of singularities and discontinuities. So it's probably quite difficult to describe analytically. And I think that's the message on why there are so few models for which we know duality transformations exactly. Because in general, I think what we will have will be things like this, which are probably quite challenging to be described analytically. Okay, so just to give you some conclusions and then leave time for questions. What we have seen was that close enough to criticality, generic one-dimensional quasi-periodic systems are associated with these local hidden dualities, local in the sense they are defined only close to criticality. And this duality manifests in these commensurate approximants in two different ways. So first through dualities between real space shifts and momentum k, and also through dualities in the wave function, as we have seen as we have just seen. And also to finish, phase boundaries we can predict these phase boundaries and actually the phase diagrams, and in some cases analytically by studying commensurate approximants. And we also can compute explicitly these duality transformations, at least in some cases, also by using these commensurate approximants. So thank you, and I will now leave time for questions.
Thank you, Miguel, for this wonderful talk. Let us thank our speaker. So I see already we have raised hands. So Moonjeep, please unmute yourself.
Okay, thanks for the very beautiful talk. So it looks like your method is very generic for many 1D quasi-periodic systems. And I think at the end, what you can calculate is this existence of this non-trivial mobility edge. So I think I'm just asking like, what would be the most dramatic thing that can happen in this localization of 1D quasi-crystal if we were to calculate this mobility edge? Like,
you mean where in which regimes we could have problems with the model? Is that what you mean?
Oh, so you see this mobility as a function of the energy. So what would be the most dramatic thing that can happen in?
You say you're saying So essentially, in one-dimensional quasi-periodic system, the only thing that can happen is these mobility edges with with energy, but nothing, not much more. Okay. Okay. Yeah. I mean, in one dimension, that's the case. We typically have these transitions between these extended and localized phases. Typically, I mean, I think it's very well understood that in general we will have these mobility edges, and I mean that I think is well understood. But what our model gives, what our method gives, is and really I would say a deeper understanding on why these mobility edges arise in generic models. So we had this full understanding for the Aubry-André model and other special models. But in general, we didn't know what was behind these mobility edges that may be highly non-trivial. And I think I mean, our approach clarified a little bit that, and actually showed the relations between these models for which we know how to describe the phase diagram in a simple way. So I think, yeah, I think that's the answer. But just to point one important thing. So these quasi-periodic systems not only have these transitions between extended and localized phases, but they may also have critical phases. Okay. So instead of having just a critical point at some specific values in parameter space, you may also have these critical phases that spread over some regime of parameters. And actually, we are working in a generalization of our model for those cases, which also works, but we have to consider some generalization. Yeah.
Okay, I see. Can I ask one more short question? Then,
Sure,
if there is
sure.
like a finite energy window of the critical state, then what would be the duality in that case? Not just single point.
Okay, I see. So you are saying when there is this critical phase, what will be the duality? You may still have, so you may have still a duality, but between critical states. So imagine that my critical phase is spanned, so this is the dual point, and my critical phase is around this dual point. But I may still have a duality between this critical state and this critical state. Okay.
Okay.
So these critical states will be self-dual, but I may still have this duality between critical states. Okay.
Okay, I see. Thank you very much. Yeah.
Yeah, you're welcome.
Okay, we have a question from Sung Jong.
Oh, thank you for the interesting talk. I have a question about, I mean, the relation between the ballet graphene twisted and your 1D Aubry-André model. So, like, I mean, as I understood in your talk, the Aubry-André model has like it has two unit cell systems. One is, I mean, two periodic systems. One is the lattice itself, and the other is the kind of on-site potential. And on the other hand, graphene has two layers. Twisted bilayer graphene has two layers, and both of them has like lattice. I mean, the kind of similar or same lattices, and they are twisted, and the interaction comes from the interlayer hopping. So my question is like, what will happen if you just use one single layer graphene and like Aubry-André model, like you imply on-site potential modulation as another hexagonal lattice twisted from the graphene layer, then is it gonna be similar? Is it gonna give the similar answer? I mean, in terms of the band structure, or like the density state, I mean, compared to the twisted bilayer graphene, and or is there going to be any difference?
Okay. Okay. So let me decompose a little bit. So first, I'm not sure if we are still not sure if this approach that we did for the one-dimensional case can be generalized to two dimensions. I mean, in that case, you will have this two-dimensional phi degree of freedom, and also, of course, two-dimensional momentum. And it's a little bit more complicated, but in the future we will work on that. So just to state that. But now coming to your question. So you are asking essentially if using a quasi-periodic potential in graphene is similar to will give you similar results to having these two graphene layers rotated on top of each other. And
yes, that's right.
Yeah, so I'm not sure, but I can give you some light on that. So actually, what's known so far, and actually it is in this very nice paper entitled Magic Angle Semi-Metals, is that you can, so what's very nice about twisted bilayer graphene is that you have this flat band regime, right, as a function. So at these magic angles, you get this very, very narrow band. And what they have shown in that paper is that by imposing quasi-periodic potential in, I would say, quite generic systems, you can also get these flat bands as a function of the intensity of the quasi-periodic potential. So this is in this paper. I can then send you the reference, but the paper is entitled Magic Angle Semi-Metals. So what I want to tell here is that you don't need to have these twists between the for instance, two layers of graphene to get these flat bands. For instance, you can also get flat bands by putting on-site quasi-periodicity to some model. Okay.
So if I re-put my question a little bit, I mean, in a different viewpoint, like if you have, I mean, in your Aubry-André's model, what will happen if you have simply two chains, right? I mean, not just one chain with the potential modulation. If you have two chains and different unit cells, and if you imply the inter-chain hopping.
So you are saying this case that I'm showing here, but quasi-periodic, right?
Oh yeah.
Yeah. So this is actually in this case in one dimension we have a deeper understanding, because I will show you in a moment the phase diagram, where we again can have these transitions between localized and extended phases in both models, okay, both in these Aubry-André-like models and in this case of the Moiré chain. But actually, to our description, these models are not that different. So notice that we will still have this let's say symmetry under these shifts between the sites in the different layers. And this is very similar both in this model with the Moiré ladder, so the Moiré chains, and in the Aubry-André model. So again, you can see just these sites in the lower layer as the maxima of the potential in the case of the Aubry-André model. So from our so if we were to apply our approach to these models, they are actually not that different. Okay, but going to your question, so if you look into the phase diagram, you can obtain also this transit. So this is actually the phase diagram for this Moiré ladder, but for some specific parameters that I'm not detailing here. But essentially, we are seeing the phase diagram as a function of this chi, because we are modulating the hoppings in a Gaussian fashion, and the Gaussian decays with this length chi, okay? And we are just seeing the phase diagram as a function of chi. And we see that we can also have these transitions between localized and extended phases, just like what we have in these Aubry-André like models. Okay, so this is I mean,
I see.
At least in 1D, I don't think they are that different, but I mean, in higher dimensions, I cannot make any claims. I would say they are also not that different, but I mean, it's just some.
Okay, I see. Yeah. Okay. Yeah. Thank you.
Yeah, you're welcome.
Okay. Do we have any further questions from the audience? Maybe let me ask something. So what about the quasi-periodic hopping? So if you just take nearest neighbor hopping model, for example, and some potential, and now if you want to put just in hopping quasi-periodicity, have you considered this, or maybe?
Actually, we are now looking more into those models now that we want to generalize to critical phases, because those models are known to have these nice critical phases, for instance. And you will have, so in those cases, you will have, again, as a function of the shift between the different sites, you will have, again, this symmetry under those shifts. So you can essentially, I mean, if you look into the energy bands, you will, again, have this invariance under when you cross the phase transitions between extended and localized phases in the same way that you have in these models. Okay, so yeah, essentially you can this approach also works for those cases. Yeah, good question. We are actually looking into more into that now.
But does this then apply also for the critical, I mean, the regime where you have a kind of extended critical regime?
Critical phase, right. Yeah, that we need to consider some generalizations. So actually, let me show you some slide here that I have of backup, which are, I mean, this is still unpublished, but just to give you some hints on what happens. Okay, so this is a little bit, let me just, so essentially what happens in the models that we've seen so far is that if you take a large enough commensurate approximant and you look into the characteristic polynomial of your system, in this limit of a large unit cell, the only terms that will survive will be cosines of k and cosines of phi. Okay, that's why you see these Fermi surfaces that are just these sinusoids. Okay, so these will be the terms that will survive. However, for the critical phase, we will have here another important term, which will be this cross term, cosine k times cosine phi. So this we didn't see in this thing that all the things that I showed you was just for extended and localized phase or transitions between extended and localized phases. They didn't include these critical phases. But then if you look into the Fermi surfaces associated with these critical phases, they will have this additional term that is a cross term cosine k and cosine phi. And if you consider it, yeah, you can still guess where there are the critical phases and make the same predictions as you did in the other cases.
Okay, thank you. Do we have any further questions from the audience? Okay, in case not, let us thank Miguel again for this wonderful talk.
Thank you.
So with this, we conclude our today's seminar.